Hello everyone. Hello everyone, and welcome back to our game network architecture class. In this learning unit, we will talk about real-time movement in multiplayer games, and I will try to show two simple little projects that work um, in terms of synchronizing movement of objects in a very simple multiplayer game. We would use time-based versus frame-based synchronization on our system, and then you'll see the difference between these two areas. Basically, when you look at setting up a Flash game here with ActionScript, and later on when you think about implementing your game engines such as UDK or Unity, you would notice that there are certain ways that you will be able to implement synchronization across your platforms and essentially on client machines and the server to achieve real-time motion or real-time movement of your game objects. Um, Basically, if you look at what is going to happen when you have a multiplayer game, your clients basically move a character on their own local system, their own local screens, by their own local um, input devices such as mouse or joysticks or keyboard. Um, but the idea is that across the game, all the other clients should receive some information about the movement of the object in one client, and to be able to render that information or the location of the or the position of the client objects, other clients' objects in their own system. Um, so if you wanted to achieve any kind of game time synchronization across your um, client machines, you would have to bring the server in and and, and somehow get the information about the state and the position and the location of the objects in every single client machine, and get them and to be able to reasonably render that information over your other clients in your network. So if you're looking at certain kinds of paths that game objects are taking, you would have objects that basically, for example, projectiles like missiles that are moving about in a straight line. So they kind of follow a very linear and simple predictive pattern of motion. You may have avatars of objects that are walking around, so they're a little bit more unpredictable in terms of their movement, but still you can access certain kinds of behaviors of your client objects to be able to kind of predict their motion. You may have a character in first-person shooters, so that movement is totally based on what your user's input on one client is. Um, and in a racing car, you have fast-moving objects, in this case cars, in the object in the game. So each of these paths need to basically create the motion on your screen in a real-time fashion. So we can think of several mechanisms to implement these movement patterns. A very simple target localization pattern or technique is to implement waypoints. A waypoint is a simple target position for your game object, and so your game travels across a line to move from its current position to the waypoint position. So what you can do is you can get the information from one client machine, predict the waypoint of the objects in control of that client machine, project those waypoints onto other machines, and have them predict a simple pattern of motion. In first-person shooters, you basically control your character by running, walking, or jumping. And so you start, stop, and change the directions very quickly. And essentially this kind of game genre requires a very responsive control system. So in a car racing game or in first-person shooter, you should be able to control the cars or the characters quickly, and it would be really difficult for so that it would be really difficult for other players to properly and smoothly infer where the objects are and where they're going to be. A very simple mechanism for you to be able to tell other clients about the position of the objects under your control in your own client machine is to simply transmit your positions. It could essentially work for slow-paced games, but and we'll see this a little bit later. But in faster games, this simply communicating the position of your objects is not going to be reasonable. You wouldn't give any good precision out of this. To alleviate this problem, we will be able to set up our information that we will be passing to the object to the other clients on the server is going to use vectors. A vector is basically a mathematical concept that integrates the position of your objects in a multidimensional space. So, for example, if you have a 30-mile-per-hour wind blowing from the east, you can integrate this as a vector whose heading is coming from the east, and then its amplitude of that vector is going to be 30 miles per hour. So you would indicate the properties of your client-controlled objects as a speed and a direction. Or essentially the amplitude and heading of your objects. By knowing the heading of all of the moving objects, you will be able to perform the predictive motion or a predictive movement that would allow you to predict where your objects will be by the time that they're going to be rendered on your other clients' machines, and then you can keep this information updated. There's another concept called line of sight, and the line of sight is very simple. If you have some original point, for example, a position of a vehicle or a gun, the line of sight is a trace or a line that goes directly from your object to its target destination. You can use AI techniques or artificial intelligence techniques in conjunction with the line of sight in your games to determine what your objects can see, and if the object, what your objects can see is another player or another game object. You can use this, for example, to use a targeting a gun in a game, in games where you have vehicles or characters that move based on a mouse click. And so this way you can essentially create a straight line path between the original point of your object, your original location of the objects, and the target point that they would have to go to. Now, when we talk about updating, essentially, the position of your objects, whether it is the position that is being communicated directly between clients and servers, or the position that has been predicted, you would be able to think of updating in two different contexts. And the first of which is the context of frame-based movement versus the time-based movement. So we would essentially make our updates occur over frame intervals or over time intervals. When you update based on frame intervals, you completely ignore the time parameter, and the position of the objects basically are updated from frame to frame whenever a frame has been passed. For example, you can update the position of a flying missile by 3 pixels in the positive X direction or by 6 pixels in the positive Y direction every frame. In a time-based movement, you update the position of your game objects based on how much time has been passed. So you have the acceleration and the velocity of your objects, and then you take into account the element of time, and then you calculate the new position of your objects based on the time that is passed and the speed at which your objects are moving. And at that point you can project that back into your image space, which then gives you an actual pixel value for the movement of your object. Frame-based movement works fine for every single player game that you can think of, because when you're dealing with single player games, the concept of time and the amount of frames that your processor on your single player computer is processing is essentially a direct one-to-one function. So if your processor is fast, it takes less time to create and render a frame compared to a slow processor. But since you're only using one processor, you're only creating a single player object or a single player game, really the concept of time and frame are identical. So in this case, you can just implement frame-based movements, which is a very simple technique. However, when you're working with multiplayer games, you would have to take into account the differences between the client machines that would be rendering your game play and your game dynamics. So, for example, if you have a situation in which you have a two-player shooter game and you're using frame-based movement, if a bullet is fired and it's traveling at the speed of 8 pixels per frame, then different hardware mechanisms would create different amount of pixel movements for your bullet. For example, if player 1 is running a faster machine that is processing at a frame rate of 30 frames per second compared to another player playing on a computer rendering a 25 frame per second contents, then over a course of 1 second, in the first class machines, the bullet travels 240 pixels, versus on the second class machines only travels 200 pixels. So this clearly contradicts between the management mechanism that your game needs to take into account to alleviate the problem of different amount of movement for the same object that's being processed by the gameplay. So essentially, frame-based movement is usually okay for games that you don't require a lot of sophisticated time synchronization between multiplayers. And that time synchronization between multiple players isn't really very important. So for this example, I'll show you how you can implement a technique that's called Here I Am technique. And basically it's a frame-based position update mechanism. And we'll see how we can control the location of a little alien on the screen, and then how other players would perceive the location of the alien that is being played by one player. And so you will see that actually the location of the actual object in your screen is going to be different than the location in the frame-based mechanism that other people would see it. But for certain examples, or for certain kind of games, it's that precision is not really that important, so you can still live with it. And then for the context of precise movement prediction and rendering on multiple client machines, we will look at time synchronization. For the time synchronization to work, we would have to create a timestamp plugin, essentially, that would take care of the heartbeats or the pulses of time that are being passed. And then we would host that functionality on the server, and then you would let the server to update the position of all the objects on other clients. So let's jump in and let's start our program that runs this little Here I Am approach, or the frame-based position update approach in our ActionScript functionality. And then we will see the benefits of frame-based mechanism, which is really the simplicity of it, and then its limitations when it comes to the precision of your update mechanism. For this example, we don't really need any kind of plugin. We essentially send the position of our objects our game objects in a public message request, and then we would let the clients to parse the messages and to update the locations of all the objects on their screens. Alright, so now we're about to write our program, or the here I am position controller, and I have the project in your Blackboard, so you should be able to download it and start programming with me. And what the project essentially does is that it's made of like all of our projects so far, ElectroServer client-side code, and all the assets and libraries that you need is also included. First thing you need to know is to open your server XML file and make sure that your IP address is 127.0.0.1 and your port that you will be communicating over binary communications with your server is 9899. So that's under the server.xml parameter file under your binary files. The next thing that you need to do is to set your ElectroServer and start it up. And when your ElectroServer starts successfully, minimize it. Make sure that you don't close it. Now let's look at the program. So the program is basically created here. And so you have a main entrance function, and your main function basically creates a new connect and login object, which is the connect and login file, action script file that takes care of creating your basic ElectroServer object, connecting to your server, and logging in, and then adds that child. Then in your connect and login file, basically you initialize your game or your connection. And in the initialization stage, you create an ElectroServer instance, you set the protocol to binary, you add your event listeners, and then when the event listener for connection has been created, you create a login response or a login request and send the login request to your server. And when your login response comes back, if it was successful, you start your game. And in the start game, basically you create a class that contains your gameplay functionality, which is here I am example, and then you call your context. So first off, we would have to create our ElectroServer object. So we would create an ES object. So we'll create a private variable ES object, and this would be of the type ElectroServer. And then we are going to connect to our ElectroServer in the file loaded section. So we call up on our ElectroServer, create connection with the IP and port. Up in the initialization function, we create an ElectroServer instance. So this would be a new ElectroServer. We set the protocol of our ElectroServer as binary, and then we add our event listeners. So add event listener, message type, connection event, and the connection event function that we have, or the event handler, is going to be on connection event. So I'm just going to copy and paste it up here, and the scope of this function is going to be the entire class. And then I add another event listener, this would be a login response. And the name of this function would be on login response for the handler, and its scope is going to be my class. So now I have my, in the initialization stage, I have my ElectroServer object created, its protocols set, and its event listeners and event handlers created. I also connect to the server by reading the IP in the port. Now I will populate my connection event handler and my login response handler. So in the connection event handler, I'm not going to add all this information in. As you see here, you basically create a login request. You populate the username of that login request by giving it the name player and then a random number, and then you send the login request to your ElectroServer. And if your connection was not accepted, then you just show an error message. Once the connection is accepted, then you call the start game function, and in the start game function, you basically set your functionality for your ElectroServer. So what we will have here is that we will create a here I am example, which is a object of the class here I am example, and I knew this object, and then I need to set its ElectroServer object onto my project level class, and then I call its initialization function, and also I add it as a child. Okay, now let's run this program, see what happens. Alright, if your program compiles at this point, you should be good, meaning that your client connected to the server, and now your function is initialized and ready to work. So now we go to the here I am example, and then we start populating the contents of this new object here. Now notice here, the here I am example class has an ElectroServer, a room, a key manager that goes through left, right, down, and up keys, which are the arrow keys. You have an array of guys. You have a guy by name, which is from the dictionary. And then you have an object my guy, just a guy for your client, and its type is guy. And then you have last time sent, which is an integer. So you add an event handler for your here I am example, and this event handler basically is the event added to stage, and when your object is added to the stage, you call up on add to stage event handler. Basically you create a key manager, and then you assign keys left, right, up, and down. This happens when your function runs the first time. Next, you create you initialize this object, which is the function that we called from our previous class, from our connection and login class. You basically initialize the guy's array, and you set your time at 0, and then you add an event listener called interFrame, and the event handler for it is going to be interFrame. You create event listeners for your ElectroServer as a join room event, a public message request event, and a user list update event. Then within your initialization section, you basically create a room request. You set the name as here I am, the zone as here I am, and then you send it to your server. We'll fill some of this information later on when we need to. In your public message event, basically you create a NEAS object. You set a string to it, and then if the string was update position, you call up the update event handler on your ElectroServer object. In this case, we only have one action, which is the update action. We don't have any other action here. In the update handle position, you basically have a string name, that is the name of the electroserver object that is being passed, and then you have two integer values, x and y, which is the x and y of the electroserver object that is coming to you. So this essentially is basically each of the guys would send an update message, and this would be the name of the action, or the name of the object, and it's x and y. If the message is sent from you, basically you set the mirror the name of the object as my underscore mirror. This way you would be able to see the shadow of your own alien on your own screen. Basically it's the location where other screens will see your object. Then you have a guy variable that you create. If it's null, you create a new object for it, you set the name of it with x and y, and then you add it to the list. If the name is your own mirror object name, you just set its alpha 0.5, so it's going to be a different shade of the guy. And then you create a you call the function on the guy if the guy is not you, so which means that on your own screen you just move the object. If it's not your own guy, then it's a shadow of the other guy, then you essentially walk that guy to its destination location. We'll see that a little bit later. The update list is practically the same as we did with the updating the list in our chat room, so that's really not a big implementation. We need to also write the enter frame event handler, which was the event handler that we created here to handle whenever a new object enters and is in need of updating the positions. So what we will see is that if the current object, the current guy, is not null, we check for keys, we check for the movement of the object, and then to see if 500 milliseconds has passed. If it has passed, we update the location. We send the updated location to the server. Otherwise, we just don't. And essentially, the move guy basically moves your object. We send the update location. So basically, you format an electroserver object, you set its name, position, x and y, and then you send it to your electroserver. Also, on the join room event, you set the room. You create a guy, set its x and y, give its name, and make it my guy, and then add it to the list of the guys. So let's go and start implementing this functionality. Alright, so we first go and start implementing the onJoin room event. Well, basically when a player enters the room, what we need to do is to set the room to e.room, and then we create a guy for that person. So we create a variable of the type new guy. Alright, and then we need to set its x and y. So we go guy.x, and let's put it at pixel 200, and then guy.y 200, and then we set its name. So we go guy underscore player name equals our electroserver object that has been connected to the server. We get user manager get me get user name. This way we'll be able to associate a unique ID for this guy, and then we just basically add this guy to the list of guys. So what's happening, we push this this new object onto the list of our objects. We set the name for it, and then we said it's me property, which basically indicates whether or not this is our own guy in the list of all the aliens that are being rendered, or it's somebody else's. So as you notice here, when we run this example, you see that the guy is being created and its location is going to be essentially in the location 200 and 200. Now if you add a new or another guy, see that the second object is also going to be created and placed at the location 200 and 200. Alright, now let's go and add some more functionalities to our objects. So now for every frame that is being rendered on the screen, we would basically need to create the event handler that takes care of what is going to happen whenever every frame is rendered. So once a frame is rendered, we need to double check and see if the list of guys that we have or if in the current context the my guy is not null. If the guy is not null, oops, I'm working in a different file here now. So in the frame, we test to see if the current guy is not null. And if it's not, we check for keys basically to read up, down, left, and right. And if the user pressed any key, we just move the guy on the screen, and then we test to see if the time minus last time sent is greater than 500 milliseconds. If it is, then we send updates. And the send update is the event handler down here. Now let's run this function and see what is going on with it. I mistyped the name of the guy, so that is the error. Right, so as you see here, I'm showing the object basically that enters, and I'm also testing for up and down keys, but I'm not actually sending the updated location of the object. So now I need to go down here and populate my send update function that basically formats an ElectroServer object with the updated location of the object, and then send the updated location to the server. So in the update function, we will create an ElectroServer object, and this would be an ES object, then would set the action for this ElectroServer object. So we have a plugin constants dot action, and we set it to update. So we go plugin constants dot update position, and then we set our ES object set integer, it's going to be a plugin constants x and my guy.x, and then ES object set integer plugin constants dot y, and it would be my guy dot y. Also, we set the name of this object to be sent, so ES object dot set string plugin constants dot name to be my guy dot player name. Then we send this electro object as a public message request to the server. So we need to create a variable of public message request. Then we set its room zone. The message would be empty because we are just sending an electro server object, so we serialize our message. So we set our public message request, set room ID, going to be room dot get room ID, and then our public message request set zone ID is going to be room.getZone ID, and our public message request set message, we just send an empty message, and then our public message request set ES object to be our ES object that we just populated, and then we send this public message request to our server. Alright, now let's run, see if we have any errors. Alright, so we don't have any errors, and then when you press the keys, nothing still is going to happen. Alright, and finally we go to our handle update position, and if the guy that is being handled is not me, I just walk to X and guy.x and guy.y. Oh, actually, let me just double check, see where I'm sending this message to. Oh yeah, I just send it to X and Y. Alright, and alright, now let's run our project. I am essentially missing a basic content here. Okay, here I see the problem. I did not set my guy here to be guy. Alright, so now my guy is set, so this should run. So as you see, when I move, on my own screen, my guy is being moved, and the shadow is where other players see my player. So let's open up another player. And so the one at the bottom was me, and the one at the 200 200 is the second player. So when they move, as you see, they're being updated on other players to the left, and then the shadow is where the other players would see their objects. Alright? Now let's see what happens if we make our updates longer than 500 milliseconds, which was basically here. Now to make it like 1 second, then the updates are going to be sent 1 second over 1 second periods. Alright, and if we make it even longer, let's say 5 seconds, so we send 500 seconds, milliseconds, the updates are going to be rendered at a later stage. So the player is facing to the left on my screen. Now when the player faces to the right, as you see, their location is being updated, but their orientation is not. As you see, it takes 5 seconds for the player to start walking properly. So the 500 milliseconds sounds to, or half a second sounds to be a reasonable mechanism or time frame for updating in our case. Right. Alright, so this is the frame-based update. I will go over the time-based update mechanism and show you a little bit about what It means to use a clock cycle and perform time-based update. And then I showed you the example of moving the alien with the time-based update, and then I would ask you to write a program as the project to work on your time-based update.